Okay, so today we are going to discuss the Jan 2020 M3 paper. Let's start with the first question. A rough disk is rotating at a constant angular speed of 5 revolutions per minute about a vertical axis. The axis is perpendicular to the plane of the disk and passes through the center of the disk. Okay. A particle P of mass mkg is placed on the disk at a distance 0.2 meter from the axis. So I hope the picture is drawn inside your head, right? So there is a rough disk. They mentioned the word a rough disk. So there is a rough disk, and then it's rotating at a constant angular speed of 5 revolutions per minute about a vertical axis. So there is a vertical axis. Okay, around the vertical axis, the disk is rotating. Okay. The axis is perpendicular to the plane of the disk and passes through the center. A particle P of mass mkg is placed on the disk at a distance 0.2 meter. So you have a particle here, it's placed at a distance 0.2 meter from the center of the disk. Okay, a particle of mass m is placed on the disk, okay, distance 0.2 meter from the axis. The particle does not move relative to the disk. Okay, the particle is staying on the disk even though, so while the disk is rotating. The coefficient of friction between P and the disk is mu. Find the smallest possible value of mu. Okay. So what do we mean by the smallest possible value? There are two scenarios here. One, they can ask you, the smallest possible value of mu. Let's first discuss that one. How do we find the smallest possible value of mu? By the way, what concept do we have here? This is what theory. You can see this is rotating, right? First of all, it is circular motion. And what circular motion are we talking? There are two types of circular motion we discussed. Horizontal circular motion and vertical circular motion. So this one is horizontal circular motion. So in horizontal circular motion, there are only two things you need to do. One is vertical equilibrium, because when you are moving in a horizontal circle, your forces are vertically in equilibrium. And the next thing you do is we apply F equal ma towards the center. So we apply F equal ma towards the center. Okay, now the thing is to find the smallest value of mu. Now think about the way that this is rotating. Now you have to decide the direction of, actually, okay, let's first mark the forces. What are the forces we have here? There is a particle on the disk. Obviously, what do we have? The mass is m. So there is the weight mg. You have weight mg. And also what else do you have? The particle is lying on the disk. So it's touching the disk, which means you have normal reaction perpendicular to the surface. Is that correct? Okay, then what else do we have? The normal reaction, the weight. The angular velocity is 5 revolutions per minute. We don't work with revolutions per minute. You will have to fix it to what? Radians per second. Okay, revolutions per minute. You'll need to convert it. Okay, so before that, we need to do that conversion as well. However, I want you all to now think about one more thing. I want you to think about the friction, because they say it's a rough disk, right? So when it's a rough disk, what do you think of when they say to find the smallest possible value of mu? So how do we find the smallest possible value of mu? Okay, so while the particle is rotating, the tendency is that the particle is going to slip outside. Okay, the tendency is that the particle will try to slip outside. It will try to go out when the particle, when this is rotating. Right, the faster you rotate, the tendency is for this to slip out. So then, because it's a rough disk, the friction will try to prevent that. So to prevent that, the friction will act where? The friction will act towards the center. So that is what we have here. So then basically, here your force towards the center will be friction. Okay, so first, so my force diagram is complete. Now let's go for the conversion of the unit. So we have 5 revolutions per minute. Convert it to radians per second. 5 revolutions. 5 revolutions. So you know 1 revolution is 2 pi radians. Isn't it? So 5 revolution is 2 pi times 5. Do you agree? 2 pi times 5 revolution is equal. 1 revolution is 2 pi radian. So 5 revolutions means 2 pi times 5 radians. Isn't it? So we have 10 pi radians. This is what? Per minute. 10 pi radians per minute. In 1 minute. So to convert it to seconds, 10 pi radians, here divide by 60. 1 minute is 60 seconds. So this is the omega. So we get omega is pi over 6 radian per second. Pi over 6 radian per second. Okay, so then let's go for the next thing. In horizontal circular motion, object is in vertical equilibrium. So for vertical equilibrium, what do we have? When we consider the vertical equilibrium, R will be, the normal reaction will be equal to the mg. Okay, then let's write the equation for the next equation. The next equation we have is F equal ma towards the center, right? F equals ma towards the center. Apply F equal ma towards center now. Okay, so let's apply. What are the forces we have towards the center? The friction. Okay, F equal ma towards the center. So the forces we have towards the center is the friction. So friction equal mass is m and acceleration. So when it comes to centripetal acceleration, we have a few equations, right? R omega and v square over r. So which one do we use here? We'll go for the one with the omega, right? Centripetal acceleration is r omega square. R omega square. Okay. So let's we have the omega value. Let's input it. The friction force. The only force we have to understand is friction. So m radius. The radius will be 0.2, right? Radius will be 0.2, and omega is pi over 6. So that will be square. So when we simplify, we get here. What do we get here? 0.2 divided by 36. 0.2 over 6 square, right? Yeah. We'll give the fraction answer. So I get here m into 1 over 180, and don't forget there's a pi square here. Okay, so just we'll keep this in terms of pi, and at the end we'll give our answer in exact, we'll give our answer in decimal. Okay. 0.2 over 36. I type 0.2 over 6 square. Okay, and that gives me, because the 6, yeah, 0.2 over 6 square gives me 1 over 180. So m into 1 over 180 into pi square. Okay, so this is my the friction force. Okay, so now they are asking us to get the smallest possible value of mu. So for this, you need to remember a little bit of m1. So in m1, you have learned the maximum friction is F max, right? The maximum friction F max is equal to mu r. So the friction that we have over here now, we don't have anything about whether it's about to move or anything like that, right? So then what do we say here? The friction we have here is less than or equal to the maximum friction. Okay, so the friction value we have here, we found that it's pi square m over 180. It's less than or equal to the maximum friction. Maximum friction is mu r. Maximum friction is mu r. So mu is what we need to find. R we just found earlier, right? Who is R? R is mg. We found earlier by vertical equilibrium. R is equal to mg. Replace R with mg. So you can cut off m to m, and you end up getting here mu is greater than or equal pi square over 180 g. So this is the exact figure if you take. So the smallest value of mu is, so smallest, because you have mu is greater than, right? So smallest value of mu is pi square over 180 g. So give it to a few decimals. What is the answer? Yeah, give the whole thing. Pi square over 180 times g is 9.8. Okay. G is 9 point. So we get 0 10 to the power minus 3. So 0 0.0055. 559. 0 0.00559. 5595. Or better write it as 3SF. 0.00560. Something like this. Anyway, you have given the exact answer, so you are safe. Okay, so this is the smallest value of mu. Okay, question number 2. A particle P of mass 0.5 kilogram is moving along the positive x-axis. At time t seconds, p is x meters from the origin O and is moving away from O. So they keep these things in your mind, okay? At time t seconds, so at any general time, they say p is x meters from the origin and is moving away from O. So it's directly going away. So there is no story about it returning, okay? Because these things are important when it comes to finding distance, displacement, those things matter, okay? So where velocity is equal to 1 over 4x plus 3. So they have given you the velocity function. And you can see here, the velocity function is the velocity is given as a function of what? The velocity is given as a function of x, as a function of displacement. So in M3, there are two major parts we learn in the first chapter. We learn about acceleration as a function of time and acceleration as a function of displacement. So those are the rules we need to use here anyway. So what we do here is find the distance of P from O when time is 2. So when time 2 seconds, how much of a distance has it traveled from O? They use the word distance. Okay, let's see. So they have given you the velocity function 1 over 4x plus 3. Okay, so what do we know about velocity? Velocity is, in other words, what? Dx by dt, right? Velocity is dx by dt. So replace velocity with dx by dt. Dx by dt is equal to 1 over 4x plus 3. So now what do we do? So since your velocity is given as a function of displacement, you don't now in these kinds of questions, you don't immediately integrate velocity to get displacement. You can't do that. That is correct if your velocity is a function of time. But when your velocity is a function of displacement, you don't immediately integrate that given velocity. That's wrong, okay? So in such situations, we replace velocity with dx by dt, and what do we do? Separate variables. Separate variables and integrate. So for example, I'll take the x terms to the side with dx. And I'll take t terms to the side with dt. So I have dx here. The 4x plus 3 comes to the other side. So 4x plus 3 times dx equals 1 times dt. You see? So integration. Let's integrate. So this side integrates with respect to x. This side integrates with respect to t. Okay, so what do we get here? 4x integration is 4x square over 2 plus 3 integration is 3x equals the integration of this side, you're integrating 1 with respect to t. With respect to t, therefore you get t. Okay, and you can put a plus c here. Okay, so then they have given us the initial conditions. They have said when time is 0, P is at the origin, which means what? At time 0, it's at the origin means x is 0. So input those limits. So x0 times 0. So what happens to C? C becomes 0. So your final equation is t plus 0. So t equals 4x square over 2 plus 3x. So basically 2x square plus 3x. Okay, so this is the, so anyway, we need to find the distance when time is 2. So what do you need to do here? Replace the x, find the distance of P from O when time equals 2. So, okay, replace the P with 2 here. Replace C with 2 here. When T equal to, replace C with 2. 2 equals to 2x square plus 3x. Okay, so we get here 0 equal to 2x square plus 3x minus 2. What do we get here? What are the factors? 2x minus 1 and x plus 2. So basically we get x equals half or x equal minus 2. So in here, now here x represents the displacement, right? X represents the displacement. Now the thing is this, they are asking us to find distance. Okay, distance means like it covers whether you go front or whether you go behind. Distance needs to be, we have to take everything. The amount you went front, the amount you came back again, we have to add everything. But displacement gives you the shortest distance. Now the thing is this, they ask you to find distance. And these equations are designed to not give you distance. These equations are designed to give you displacement. However, they have given you one key thing here. What is it? They say the particle is moving away from the origin. Always moving away from the origin. And also You have 1 over 4x plus 3. I mean, this function is flying ahead, it's increasing. Okay, so basically what you need to understand is they have told it's moving away from origin. Basically, distance will be equal to the displacement. If you are moving only forward, distance and displacement will be equal, right? Okay, so then in that case, you need to understand x equal minus 2 is not what we need to take. We need to take x equals half. So correct answer is x equals half. Okay, let's move on to the next part. Find the magnitude of the resultant force acting on P when time equals to 2. Okay, how do we find the magnitude of the resultant force? So obviously to find force, we need to use what? F equals ma. To use F equals ma, what do I need to find? I have to find the acceleration. So how do we find the acceleration? So for acceleration, there are two equations we learn in this particular chapter in M3. One equation for acceleration is acceleration equals to dv by dt, right? And the other, that is when your acceleration is a function of time. The other equation you use is acceleration equal v dv by dx. This is given when your acceleration is a function of displacement. Okay, so these are the two equations we use. Acceleration is dv by dt or acceleration is v dv by dx. Okay, so then we already have okay, so what we can do here is we can use this equation. The velocity is there. dv by dx, we can find it, right? Can't we find dv by dx here? Yeah. Okay, let's find dv by dx. We can't use acceleration is dv by dt, by the way. Okay, we can't use it because of acceleration. This is not a function with time. It's a function of displacement. So this one we can remove. Let's find velocity equal 1 over 4x plus 3. So dv by dx, how do we get dv by dx? I think I prefer to differentiate, and we can use quotient rule here. Okay, or else I can take this up 4x plus 3 to the power minus 1, and we can take, we can differentiate dv by dx equals, so now we can use the power rule. Minus 1, 4x plus 3 to the power minus 2 into 4x differentiation is 4. You are completely, it's completely fine to use the quotient rule if you want. Okay, so basically this gives me minus 4, and I take the 4x plus 3 down. 4x plus 3 to the power 2. This is dv by dx. So let's input the value into the equation. Acceleration equals to v dv by dx. V is 1 over 4x plus 3 times dv by dx is minus 4 over 4x plus 3 square. Okay, and then what do we need to do here? Find the, so we need to find the magnitude of the resultant force acting when time is 2. Okay, so let's find the resultant force when time is 2. So when time is 2, I think you have your x value here. When time is 2, what's our x value? Our x value is half, which we found earlier. So input the x value half. Minus 4 over 4x plus 3 to the power minus 1, right? 4x plus 3 to the power 3. 4x plus 3 into 4x plus 3 square. Input x as half. Minus 4 over 125. Minus 4. So they want to find the magnitude of the resultant force. So to find the magnitude of the resultant force, what do we use? We use F equals ma. The mass is given, right? Mass is 0.5 kilograms. So they want the magnitude. So when they want the magnitude of the force, do we need to take the positive, negative? No, just give the size of it. Okay, so mass is 0.5, and for acceleration, just use 4 over 125. You don't need to use the negative. The acceleration is negative, means it's a deceleration. But however, all you do is use just 4 over 125. And what do you get here? Magnitude of the force. We get 2 over 125 newtons. So it's 2 over 125 newtons. Okay, question number 3. Figure 1 shows a hemispherical ball of internal radius A fixed with its open plane face uppermost and horizontal. The lowest point of the ball is A. A light inextensible string of length A root 3 has one end fixed to the point B, where B is vertically above A and AB is 2A. A particle P of mass M is attached to the other end of the string. The particle moves in a horizontal circle on the smooth inner surface of the ball with constant angular speed omega. Okay, so this is moving with constant angular speed omega. The string remains taut and the particle remains in contact with the ball throughout the motion. So they have actually marked the path of the path of the particle. Can you see in dotted lines? They shown you how the particle is moving around the ball. So this particle is moving in it moves in a horizontal circle. Okay, on the surface of the ball, you can see they have marked here with the two arrows. It shows the path of the particle. So they're asking you find in terms of M, A, omega, and G the tension in the string. Okay, so before we find the tension in the string, I mean, what is the first thing we need to mark all the forces. So what are all the forces we have? So number 1. So first thing that we have here is the tension, right? So we have the tension in the string. Next thing is they haven't told us, they have told us the mass of the particle is m. So that means we have the weight mg. Okay, we have the weight mg. Okay, and then there's one more important person that we need to mark, and that is the normal reaction. So now you have a very important thing to do here. You have to mark your normal reaction. Take a few moments and mark the normal reaction first, and then I will show you how I mark it. Okay, so then the normal reaction. Now, when you mark the normal reaction, normal reaction is always supposed to be what? Perpendicular to the surface that we are touching. So when we draw a perpendicular, now this object is touching this hemispherical ball, right? So then to the hemispherical ball, so from any point in any point in a circle, when you a sphere, if you draw a perpendicular from the surface of the sphere inside, where do you think it will definitely pass through? It will definitely pass through the center of the sphere. Okay, so the normal reaction, you just can't draw it anywhere you want. It must pass through the center. So this is the normal reaction. Okay, so the normal reaction must go through the center of the hemisphere. Be careful. Okay, so there is a center of the hemisphere, and you also have the particle P moving in its own circle just below the rim of the hemisphere. Okay, so the normal reaction that we make, because we're touching this curved surface of the hemisphere, the perpendicular that you draw to a curved surface of the hemisphere will definitely pass through the center of the hemisphere. Okay, so then the next thing you need to notice is that you have the center of this own circle, right? Now this particle P is moving in its own horizontal circle. So that circle also has its own center. Okay, so have that also in mind. Okay, so now let's find the angle. How do we find the angle? The first thing is they're telling you that the internal radius of the ball is A, right? So the internal radius of the ball is A means now you know that this point here is the center of your hemisphere. This point, let me name it as O. So this point O is the center of your hemisphere, which means from this point O to any place on this circular surface, the radius is A, which means from O to A also the distance is A. Are you with me? O to A distance is A. Who else? O to P is also A. O to P is also A. Is that okay? And what else do we need? And then they have told us the length of the string is given, right? Okay, they have told AB is 2A. Okay, AB whole length is 2A means what? AB whole length is 2A means we know O to A is A, which means O to B must be A, another A. Then AB is giving us 2A, the whole length AB. And then they've told us another extra thing. They've told us that the length of the string, a light inextensible string of length A root 3 has one end fixed to be where, okay, and the other end is at this point. So the length of the string is what? A root 3. So mark this as A root 3. This length is A root 3. Okay, so now you have the task of what? You have the task of finding the angle. Okay, how do we find the angle? Okay, how do we find the angle? Okay, so one method is you could use the cost rule, or you could even use the cost rule for this BOP triangle and find the OPB. You can find the angle OPB. Or else I can actually see a right angle triangle here. If you look at this B, P, and if you look at the point that the center of the circle where the particle is traveling, not the center of the hemisphere, but I have taken this point down here. Okay, so we can't take that, right? No, we can't take that because we do not know this short distance. Yeah, we do not know this distance. Yeah, so I think, yeah, we'll have to go ahead with cost rule. Right, we'll go ahead with that. Okay, so we can't use the right angle triangle that we have here because we do not know this length O2. Let's say this is X. Let's say this point is X. So because I don't know the OX distance, I can't use the right angle. Yes, we'll have to use the cost rule for what? We will have to use the cost rule for the OBP triangle. Shall we use that? Okay, so when we do that, I have written the cost rule over here. So let's find this angle. I'll name this angle as theta. So let's find cos theta. Cos theta equal B square plus C square are the two adjacent sides, right? A square plus A root 3 square minus the opposite angle is this one, right? These two are the B and C. This is the A. So A square, this A square plus A root 3 square minus A square divided by twice of the two adjacent sides. So twice of the two adjacent sides to the angle, which is A and A root 3. So then here I can see plus A square minus A square will cancel. I end up getting here 3A square, right? Root 3 squares to give you 3, and A square is coming on top. Down below I have 2 root 3A square. So A square to A square cancels and we have cos theta, and you know definitely here theta is definitely an acute angle, right? The way I'm marking, you can see it's an isosceles triangle. OBP is an isosceles triangle. Theta is acute. Cos inverse of 3 over 2 root 3, actually 3 over root 3 is root 3 over 2. So anyway, what is the cos inverse of 3 over 2 root 3? 30 degrees. So your theta is 30 degrees. Do you realize? So this theta is 30 degrees. So if this theta is 30 degrees, the next thing you realize is OBP is an isosceles triangle, which means what? The angle at B is also 30. The angle at B is also 30. And then this is a 90 over here. This is a 90 over here, which means this big angle down here should be what? This is 30, this is 90. So in my right angle, I'm talking about this right angle now. So in this right angle, this big angle will be 60, right? This is 30, this is 60. The big angle, and this is already having a 30 here, which means the small angle here must be 30. Is that clear? There are so many drawings to do here. So this small angle here will give you a 30 degree. This is a 30 degree. I hope it's clear with everyone. Okay, so this is 30 degrees. So it's a challenge to mark all these angles, but you need to mark all the angles so that you can resolve. Because after marking all the angles, now only we can resolve. Because all we have to do here is to find the tension. So it's a horizontal circular motion. All you have to do is apply a vertical equilibrium. Up and down forces are equal. And you have to apply F equal ma towards the center. So shall we do that now? So to this question, let's apply up equal down. So what do we have for vertical equilibrium here? Shall I move the screen to the other side? So what do we have for vertical equilibrium here? So vertical equilibrium, you will have to resolve what? There are two people to resolve. You have to resolve the T and you have to resolve the R. Okay, so T. So T, how do we resolve horizontal vertically? So this big angle is 60, right? The big angle is 60 here. Okay, the full angle. So T sine 60. T sine 60 plus. What about the R? Resolve the R also. R not towards the angle to the horizontal is 30. So then it's going to be R cos 30 or sine 30. I want to get vertical. So it will be, I want to get the vertical. It should be R sine 30. If you take R cos 30, it's a horizontal component. So R sine 30. T sine 60 plus R sine 30 is equal to mg. So this is your first equation. This is your first equation. Then let's apply F equal ma towards center. I think before we apply F equal ma towards center, we need to find the radius of the internal circle that the particle is traveling. Do you notice that the particle is traveling on its own internal circle inside the hemisphere? So I need to know the radius of that path. What is the radius of that path? The radius of the circular path. Radius of circular path of particle of P. So it's going to be what? A cos 30, right? Or you could say A root 3 cos 60. Because this big angle is 60, you could say it's A root 3 cos 60. This one. Or you could say it's A cos 30. So any of them are fine. R is equal to A cos 30. So what is cos 30? Cos 30 is root 3 over 2, right? So radius is A root 3 over 2. Okay, so this is the radius of the circular path of our particle. Now let's apply F equal ma towards center. What are the forces we have towards the center? So resolve. Now center means what? Is it the center of the hemisphere? No, when we say F equal ma towards center, it means the center of our circle. So our circle is what? The circle followed by particle P. The center of that circle is the one that I marked X here. The center of the circle that I am referring, if the center that we refer here is the X, because we don't need the center of the hemisphere, we need the center of the circular path. The horizontal circular path center is what I named here as X. So let's resolve towards forces towards that center. What do we have? Resolve first R cos 30 plus the tension T cos 60, because the full angle is 60. Okay, so those are the two forces, right? We don't have anyone else who is even opposing, right? Mg is perpendicular, mg is vertical, so it doesn't count. Towards the center, what do we have? F equal ma. Mass is m. Mass is m, and the rate F equals m, and the acceleration that we use is the centripetal acceleration, right? So we normally use what? R omega square or v square over r. So they've given us, I think, omega, right? They've given us in terms of omega. Yeah, omega is omega. So we can use m r omega square. Okay, so we are supposed to find, they're asking us to find the tension, right? So let's just simplify r cos 60. Sorry, r cos 30 plus t cos 60 equals m into r is a root 3 over 2 into omega square. So I need to find t, right? I need to find t. So what I'll do is, from both the equations, I'll make r the subject. So basically in the first equation, I'll keep r sine 30 is equal to mg minus t sine 60. And in the down equation, I'll keep t cos sorry, r cos 30 is m omega square, am omega square, root 3 over 2 minus r cos 30. Is that okay? Am omega square root 3 over 2 minus r cos 30. Okay, so now what I'll do is shall we multiply the whole equation by 2 also? Ah, yeah, minus t cos 60. Sorry. R cos 30 is here. We take the minus t cos 60 to the other side. Yes. Before I go to do anything, I'll remove this 2 here by multiplying everyone with 2. So it removes the complication. So when I multiply with 2, I get here 2r cos 30. The whole point of multiplying by 2 is to remove this denominator 2 here. I get root 3. Shall I put root 3 in front? Root 3 am omega square minus 2t cos 60. Okay. So these are my two equations. And now you know what I'm going to do? I'll take these two equations. I want to find t, right? So what I'll do is I'll take these two equations and I'll divide them. You can substitute also. There are many ways of doing. I will just divide them. So I get here r sine 30 divide by 2r cos 30 equals to mg minus t sine 60 divide by root 3 am omega square minus 2t cos 60. So now it's a matter of simplifying. You can see the reason I made r the subject is now when I divide, I can cut r and r. Can you see? Sine 30 over cos 30 is tan 30. Sine 30 over cos 30 is tan 30. And there's a denominator, do not forget the 2, okay? mg minus t sine 60 root 3 am omega square minus 2t cos 60. Shall we cross multiply? And our task is what? We need to make t the subject. So make t the subject. Root 3 am omega square tan 30 minus 2t cos 60 tan 30. Multiplying this with 2, we get 2mg minus 2t sine 60. I took the 2 to the other side and multiplied the whole thing with 2. I have now bring all the t terms to one side. So I look at this, I'll take this to the other side. It's entirely up to you, right? Shall we simplify this first? Tan 30 is root 3 over 3. Okay, it comes in the color as root 3 over 3. Or basically, it's 1 over root 3. And then this one minus 2t times cos 60 into tan 30. Directly time it. Cos 60 into tan 30. Cos 60 is half root 3 over 6 equals 2mg minus 2t sine 60 is 3 over 2. Okay, so we can simplify things a little bit here. For example, I could cut the 2 and 2 here. This 2mg I don't need to do. This 2 and 6 I could cut with 2 times 1, 2 times 3. Here, if you guys can see here, root 3 multiplies to give you a 3, a complete 3. That 3 and this 3 cancels. And you're only remaining with what? Am omega square. The 3 over 3 cancels. Minus t times root 3 over 3 equals 2mg minus root 3t. Do you agree with me? I'll multiply the whole equation with 3. So I get here 3am omega square minus t root 3 over 3 into 3. The 3 cancels. 2 times 3 you get 6mg minus 3 root 3t. So I'll take the minus 3 root 3t here. And take 3am omega square to the other side. I end up getting here plus 3 root 3t minus t root 3 equals 6mg minus 3am omega square. Do you agree with me? So So 3 root 3t minus 1 root 3t is 2 root 3t. So divide the whole thing by 2 root 3. Let's take the common things out and let's rationalize. It leave the final answer simplified. So what's the common thing? I can take a 3 out. I can take a m out. So I remain here with 2g minus 3 and m goes out. I remain here with a omega square. This is simplifying a little bit further over 2 root 3. So if you want, we could multiply both up and down by a root 3. Rationalize because we normally don't leave the answer in the third denominator. So I get here 3 root 3m 2g minus a omega square. 2 root 3 into root 3 is 2 times 3. It's 6. Basically 3 will cancel off here. Right? So I end up getting a tension equals root 3m over 2g minus a omega square. Okay. Okay, part B, they said show that omega is greater than or equal root 2g over 3. So this is something that commonly comes up in your exam. Okay, in other papers also we see them asking you to prove this inequalities in the circular motion question. Okay, whenever they give you something like this, all you have to do is refer the forces you have here that contribute to the circular motion. What are the forces we have here? We have mg, we have tension, and we have normal reaction. Now, out of all these three forces, okay, you can see tension. Now, since the object is weighing down, the tension is there any chance that the tension will, is there any chance for the string to actually become slack? No, right? There's no situation here like that because the object is going in a horizontal path and it's below the object. Now, do you see that the normal reaction here is a little bit sensitive than the tension? Because the normal reaction, do you see that the circular motion here mainly depends on the normal reaction? Why is that? Because it's the normal, I mean, the circular motion, the horizontal circular motion is performed on this hemisphere while the object is touching the hemisphere, right? So it's this touch that gives this normal reaction. So if by any chance you go far, you go slower or something, the particle, if you lose the contact, do you see that you will not have the horizontal circular motion? So in order to have this circular motion, what is the most important thing? This normal reaction, it must be in contact. The object must be in contact with this surface, which means what? Your normal reaction must be greater than or equal 0 because your tension is anyway greater than or equal 0. There is no doubt about it because of the weight. The tension is definitely there. But the normal reaction is a sensitive one because if in an event the normal reaction becomes 0 or if it loses the contact with the hemisphere, you lose the circular motion. Do you get it? So in order for the circular motion to work, your normal reaction is what you need to set as greater than or equal 0. Are you with me? So now what we need to do here is what? We found the tension. So now we will have to find the normal reaction and then you can set the normal reaction to greater than or equal 0 and you can get this inequality. Okay, so let's get the normal reaction. So use one of the two equations. I'll use the first one, right? R sine 30 equal mg minus T sine 60. R sine 30 equals mg minus T sine 60. Let's input the values and make R the subject. Shall I try the sine 60 first? Sine 60 times T is root 3m over 2 times 2g minus a omega square. And I input the value sine 30 is half. Sine 30 is half. R into half equals mg And on the value sine 6 is root 3 over 2, right?
Yeah.
The root 3 over 2 m 2g minus a omega square. So simplify here, I get r over 2 mg minus, this is root 3 is 3 over 4 m times 2g minus a omega square. So I end up getting here r over 2 equals mg minus 3 over 4 m into 2g is how much? 3 over 4 into 2 is 3 over 2 mg, right? Minus into minus, then I get plus 3 over 4 ma omega square. 3 over 4 ma omega square. So r over 2 mg minus 3 over 2 mg is, we get 1 minus 3 over 2 is minus 1 over 2, right? And then multiply the, take the 2 to the other side. So r is equal to 2 into minus half is minus mg. 3 into 3 over 4 into 2 is 3 over 2 ma omega square. Do you see what I did here? I took the 2 to the other side as a multiplication. I took the 2 to the other side as a multiplication. So now I have found r. I have basically found r. So now what do we need to do? We need to set this. We need to set this on. R should be what? Greater than or equal 0 in order for the circular motion to work. I mean to continue. So taking minus mg to the other side, 3 over 2 ma omega square greater than or equal mg. M is a positive constant, right? Mass, inequality signs, it's sensitive division by negatives, but m is a positive constant. So I can divide both sides of the inequality by the positive figure m. We need to get the show that for omega, right? So then omega square, I think you can see we can take 2g over 3a. All of these are positive constants. So is this to show that omega is greater than or equal root 2g over 3a? So I think we have to show that. So we get here, then the next step, omega is greater than or equal root 2g over 3a, which is our show that. A light elastic string has modulus of elasticity 2 mg and natural length L. One end of the string is fixed to a point A on a rough plane inclined to the horizontal at angle alpha. Okay. Once again, a light elastic string. Do you see the word elastic? So elastic means the string will stretch, right? So that means you have the you can use Hooke's law. It has modulus of elasticity lambda is 2 mg. So I will mark all those important things. Natural length is L. One end of the string is fixed to a point A on a rough plane inclined to the horizontal at an angle alpha, where sine alpha is 3 over 5. Sine alpha is given 3 over 5. So immediately I can find cos alpha, or I think by experience you may now know if sine alpha is 3 over 5, cos alpha should be 4 over 5, because it's a 3, 4, 5 is the Pythagoras pair, or else you could just draw this triangle alpha. Sine is opposite over hypotenuse. Using Pythagoras theorem, this side becomes 4. So cos is 4 over 5. Basically, you need cos alpha and sine alpha. Then a particle P of mass m is attached to the other end of the string. Okay, so you have this elastic string. One end is attached to the plane. One end is attached to a point A on the plane, and the other end, a particle of mass m is attached to the other end. Okay, so how do you think is it visualizing in your head how this is working? This is your inclined plane. This is our inclined plane. This is the angle alpha. So one end is fixed to a point A. So let's say this is point A, and the other end has the mass m, right? Initially, P is held at rest on the plane at the point B, where B is above it. Can you imagine what's happening here? Now A, at the point A, they have fixed the string. Okay, at point A, they have fixed the string to the plane. Okay, let me try to mark it properly. Okay, and then it's basically a string. So what they're saying here is the initially P is held at rest on the plane at the point B, where B is above A. So you have B above A and AB is half A. So for starters, now you know your natural length is L, right? So then they are keeping it at a distance half L above A. Half L above A. So is the string stretched or is it slack? It's slack, right? Because it's a half L distance. The string is slack and this is the point B. So AB is half L. AB is half L. The string lies along the line of greater slope of the plane. Okay, that means the string is on this plane. Okay, parallel to the plane. The particle P is released from rest. Okay, so the particle, you are releasing this particle from rest. So what do you expect now? Is this a rough plane? Yeah, it's a rough plane. So anyway, when you release this particle, what do you expect? It will start sliding down. It will start sliding. It will pass the point A, and it will keep on going down. You understand? It's going down. It will have kind of like an acceleration, right? It's not going to go with constant velocity. So it will have probably some kind of an acceleration. It will go down, and you do realize it's an elastic string, which means what? It will come passing. It can go beyond its own natural length, right? It can go a little bit beyond its natural length because it's an elastic string. Okay, so they are saying the particle is released from rest and moves down the plane along the line of greater slope. The coefficient of friction between P and the plane is mu, where mu is less than tan alpha. Okay, given that P comes to instantaneous rest at the point C, where AC is equal to L plus C. So you do realize that definitely the particle, when it moves down, it should definitely go down passing its natural length, as I told you. And since it's elastic, now we know when you're moving down, it's accelerating down. And then it comes to the natural length, it doesn't stop until it comes to the natural length, it will keep on accelerating. And then once it reaches the natural length, then the string starts to stretch. And then the string starts to stretch, and then you will slow down until you come to the limit of the string, right? So that is E. Is that okay? So when I draw this particle, this goes to the other side. So we'll say this length is L. This length is the L. And let's say this length is the E. Okay. So this is the point C, the maximum distance that the particle goes below the plane. Show that mu is equal to this particular equation. Okay. How do we get this show that now? And what is the principle that we are using? So what is the main principle we use here? The main principle we use here is we use the, by the way, is the energy conserved here? So we are going to use energy principle. The main principle we use is energy principles. That is the easiest way to get it done. Okay. So in here, do we have a case where energy is conserved, or do we or is energy lost due to some external force? It's a rough plane. So there is a non-gravitational external force acting on your object, which means what? The energy is not conserved, which means you have to use the work energy principle. What's the work energy principle? The change in energy is equal to the work done by the external force, right? Or what is the external force here? Work done by friction. This is basically M2. Work done by friction is equal to change in energy. Change in energy is the final energy minus the initial energy, because definitely, no, not final minus initial. It's initial minus final, because initially you have the large amount of energy and some amount of energy is lost due to friction. So final energy is definitely lower than the initial. So then where the change in energy should be what? Initial minus final. Okay, let's talk about all energies that we have here. So let's talk about the initial energy. Okay, so we'll work it out separately and then put to the equation. Okay, so what is the initial energy? So for initial energy, what do we need to consider? What are the energies we have at B? Now, when it comes to energies in M3, we discuss three types. What is it? Kinetic energy, potential energy, and elastic potential energy. When you have elastic string, if the string is stretched beyond its natural length, you have elastic potential energy. So at the point B, now, before using potential energy, you need to use a GPE 0 level. So I'll consider this down level as GPE 0. Is that okay? Shall I move the particle to the corner here? Okay. Okay. So now, what is the G? So I will consider this down. I will take this down the lowest line as a GP 0 level. Okay, and then let's work out the energies we have at the very top. They say they are releasing it from rest, right? They are releasing it from rest. It's held at rest on the plane at the point B. So what energy do you have at B? You have GPE. You have gravitational potential energy. Do we have elastic potential energy? No, the particle string is slack. In a string, you only have elastic potential energy if the string is stretched. So at point B, we only have GPE. Let's find the GPE. So GPE is mgh. So mass is m. Is it m? A particle of mass m. Mass is m. Okay. So m into g into what is the perpendicular height? So what is the full height here? Add all of this. So you have to take this full height and then you have to resolve and get the perpendicular height, right? So this is your perpendicular height. So the full length is E plus L plus half L. L plus half L is 3L over 2. Yeah, 3 over 2L. 3 over 2L plus E is this full length. So 3 over 2L plus E is the full length and you have to resolve it to get the horizontal. Not the horizontal, the vertical. So then when you resolve it towards the angle, it's a cos. This one will be sine. So you get here H is what? 3 over 2L plus E is the full length of the hypotenuse and that is that into not cos but sine alpha. If you take sine alpha, you get this distance. Cos is going to give you this. Okay, so this full length CB, the entire CB length, this is CB cos alpha is the horizontal length. CB sine alpha, I've taken CB sine alpha. CB is 3 over 2L plus E. Okay. So let's input the value. That is 3 over 2L plus E times sine alpha. Input the sine alpha value. Mg into 3 over 2L plus E into sine alpha is 3 over 5. So what do we get here when we simplify? We get here 3 over 5 mg 3L over 2 plus E. Let's just leave it like this for now and we'll go for the extra simplification afterwards. So initial energy is done. Now let's go for the final energy. So where do we have the final energy? At the point C. So let's go for final energy. So final energy is at the point C. What do we have at point C? Do we have kinetic energy? When you add it comes to this point and it comes to rest, right? So there's no kinetic energy. Do we have gravitational potential energy? No, it's at GP 0 level. Then the only thing we have here is what the string is stretched and therefore we have what? Elastic potential energy, which is found by the formula what? Lambda x square over 2L. Lambda x square over 2L is the equation for elastic potential energy. So let's input the value. Lambda was given to us, right? Lambda was 2 mg. 2 mg into x square is Yeah, X is the extension. So your string is stretched by the factor E. Over twice the natural length. Natural length is the same thing, L. Natural length is L. So the 2 to 2 cancels. I get mg E square over L. Okay. So then let's apply the equation. Before that, we'll find the work done by friction also, right? So what is the work done by friction? Work done by any force is what? Work done by any force is the force multiplied by the distance you move along that force. Force multiplied by the distance that you move in that direction. So what's the force we have? The force we have is friction force. Friction force should be multiplied by the distance. What's the distance we have here? The object has moved along the plane, the distance BC. So what's the full distance BC? L plus half L plus E, 3 over 2 L plus E. So what's the friction? Friction is mu R, right? So friction is because we have the maximum friction here because the object is moving. The object is moving, we have maximum friction. So mu R friction. What is the normal reaction here? So when the object is moving, what's the maximum, the normal reaction will be equal to what? Downwards you have the mg, and you understand that this side will be mg cos alpha, right? These are M1 mechanics. Mg cos alpha. R will be equal to mg cos alpha. R is equal to mg cos alpha. So replace R mu times R is mg cos alpha times 3 over 2L plus E. Cos alpha we found it as what? 4 over 5. Mu mg, it's 4 over 5. I'll put it at the beginning. 3 over 2L plus E. So we are done. We have found everything we need. All we need to do is now input it in the equation and get the show that. So let's get the show that. Work done by friction is equal to the initial energy minus the final energy. So work done by friction is 4 over 5 mu mg times 3 over 2 L plus E. Initial energy is 3 over 5 mg times 3L over 2 plus E minus final energy is mg E square over L. Okay, so now work towards getting the show that. The next thing we can do here is we could cut off the mg, right? Everyone has mg. Remove mg. And then I also thought of multiplying. We need to make mu the subject, right? Yeah, we need to make mu the subject. That's what we need to do. We could multiply the whole thing with 5. We could multiply the whole thing with 5. We are targeting on making L the subject. First, we'll multiply the whole thing with 5. So I get here 4 mu times 3 over 2L plus E equals 3. The 5 removes. 3L over 2 plus E minus 5E square over L. Okay, so now let's simplify here. Taking the common denominator here, I get 3L plus 2E over 2. This side I get here 3 times 3L plus 2E over 2. This side I get 5E square over L. I think before I move this to the other side to make the subject, I need to simplify this side, taking the common denominator with 2 and L, right? So 2L is a common denominator, which means this 3 should be multiplied with an L, right? Because I have to multiply this with L. And this one I will multiply up and down with a 2. Is that okay? So I get here 3L times 3L plus 2E minus 5 times 2, 10 is square. I took the common denominator as 2L. So this one is multiplied by L, this one is multiplied by 2. And this one, the 4 and 2, I could actually cancel it out, right? So I get here 2 mu times 3L plus 2E. Okay, then we can simplify this now. 9L square 3 times 2, 6LE minus 10E square. Yeah, this 2L, and we can take to make mu the subject. This 2 and 3L over 3L plus 2E comes to the other side. And this is to show that, right?
Yes.
9L square plus 6LE minus 10E square over 4L times 3L plus 2E. And this is just show that. Okay, part B, given that E equals to 1, find the magnitude of the instantaneous change in the acceleration of P at C. Okay, so what do you mean by that? Now you do realize here that your object comes down from this point B, it comes down accelerating until it comes with natural length, and after that it starts to slow down, right? Because you're stretching the string, and then you come to this point C where it's instantaneously at rest. And then what happens? The particle always wants to come back to its natural length. That's the tendency. It wants to come back. So then it comes to this point. This is the maximum point where it stretches, and then it wants to go back. It wants to go back up again. So then they ask us to find the magnitude of the instantaneous change in acceleration. Basically, the acceleration when you come to when you reach point C and it's coming down, and the acceleration at point C when you're going to go up. So they're asking you to find that change. What is the change in the acceleration? Okay, so basically you have to find the acceleration at point C in two instances. One when the particle is coming down at the very last point, and one when the particle is about to move up. Okay, so then the first things first, we need to first consider the object is coming down. Let's consider the object is coming down. So when the object is coming down at point C, what are the forces that this object has? Now let's consider that the object is coming down, right? It's on its way down and it reached point C while coming down. So what are the forces we have at point C? Remind me again. We have the weight. We have the weight. What else? We have the normal reaction. We have the friction. Now I'm considering this coming down. Okay, I'm considering this coming down. At the moment it reaches point C while it's on its way down. So what do we have? We have the friction. The friction is acting which way? When it's coming down, the friction is acting upwards. So this is the friction. Let's say this is F1. Friction 1. What else do we have? These are three forces we have, right? So basically I want to now find the acceleration at this point. Okay, so let's find the acceleration. So friction, of course, we know friction is mu r, right? Did we find friction by any chance in the earlier question? Yeah, we have the equation. Friction is mu r, and the mu value also we did find in some manner, right? Okay, friction is mu r, which is mu mg cos alpha. Let's write it down. Friction equals mu r. R was mg cos alpha, right? Because you resolve this mg cos alpha, and don't forget there's also mg sin alpha. Okay, let's keep it like this for now. No, we'll put the cos alpha value. What was the cos alpha? Mu mg cos alpha is 4/5. So mu value I'll input it later because we have this big expression here. 4/5 mu mg. Okay, okay. Let's work on the value. Yeah, and also we can't forget that we have our string here, right? The particle is attached to the elastic string, and you also definitely have the tension in the string. The tension in the string is acting up. So I don't need to use F1 here because we have simply one friction here, right? We simply have the maximum friction here. Okay, 4 over 5 mu mg. Okay, let's find everything here. Now, I might ask is to find this acceleration. So let's find to find the acceleration. Do we know the tension? Let's find the tension also. Let's find the tension also. Tension equals lambda x over L, right? What was the lambda value? Lambda is 2 mg. 2 mg. What is the x value? X is the extension. The value that your string is stretched beyond its natural length. That is E, right? E over L. I think they have told us E is E is equal to L, which means if E is equal to L, 2 mg L over L, which means L to L cancels. Tension is 2 mg. Tension is 2 mg. Actually, we could find the value of our mu also. Let's replace the E with L and find the mu value. We can get the mu value by replacing E with L here. Replace 9L square plus 6L into E is again L, which gives us what? 6L square minus 10 E square is L square. Over 4L times 3L plus 2E becomes 2L. Are you with me? So what do you get here? 9 plus 6 is 15. 15 minus 10 is 5L square. Over 3L plus 2L is 5L. 5L into 20L, 5L into 4 is 20L square. Square cancels and you get mu is 1 over 4. So you get a mu value nicely, right? We actually get a simplified answer for mu. Mu is 1 over 4. So input that value. 4 over 5, mu is 1 over 4 mg. 4 to 4 cancels, 1 over 5 mg is the friction. Okay, 1 over 5 mg is the friction. Okay, then let's now, we are done with everything, right? We have the tension, we have the friction. So all you have to do is now what? Use the equation and find the acceleration. Let's find the acceleration when it's on its way down. So we'll apply F equal ma when it's on its way down. What do we get? The forces acting down are what? Along the plane, the forces that are acting down now, mg sine alpha minus friction minus tension, right? Equals to mass m and acceleration is what I'm trying to find. So mg sine alpha was 3 over 5. So am I correct? Friction is 1 over 5 mg. Tension is minus 2 mg equals ma. M will cancel out. Can I know the value in terms of g? 3 over 5g minus 1 over 5g minus 2g. 3 over 5. 3 over 5 minus 1 over 5. That is 3 over 5 minus 1 over 5 minus 2. Which gives me minus 8 over 5. Is that okay? Check on this again. Sine alpha minus friction minus tension. Okay, let's find the other acceleration. So what is the other acceleration? What's the only difference? Now when the particle comes down at point C and the other one is when the particle is it reached point C and now it's about to move. It's about to move up. Can you tell me what's the difference that you can get in this diagram? When the particle is about to move up. Do we have a big difference in this diagram? No, right? Tension is still the same because you're at the same point. You just came down and now you're about to go up. So what's the only difference now? The tension won't change. The mg sine alpha will be the same. Weight compounds, everything is the same. It's just that the friction will change its direction. Do you agree with me? The friction that's over here, because when you're about to go up, so now it's opposing the direction of moving up. So friction is now acting down. That's the only difference. So you don't need to draw another diagram. Just identifying the friction acts on the other side is all you need. So now applying F equal ma upwards and realizing that what? Only tension is acting up. The mg sine alpha and friction are now opposing. Do you realize what's happening here? Tension is acting up. The mg sine alpha is anyway down. The friction is now acting down because you're about to go up and the friction is opposing that. So tension is 2 mg minus mg sine alpha is, sine alpha was 3 over 5, right? Minus friction we found as 1 over 5 mg equal ma. A will cancel out. M will cancel out. So 2 minus 3 over 5 minus 1 over 5. How much is it? 6 over 5 G equals A. Did all of you come to this point? 6 over 5 G equals A. They are asking us to find the magnitude of the instantaneous change in your acceleration, right? So they are asking you to find the magnitude of the instantaneous change. Now you can see here, the magnitude of the acceleration is what? When you came down, ignoring the negatives, and what's the magnitude? It's 8g over 5. What's the magnitude of the acceleration when you're going to go up? 6g over 5. So then they want you to find just the magnitude of the difference. I mean, what's the change in acceleration? So change in acceleration. What's the change in acceleration? Just take the difference of the magnitudes of the acceleration. Okay, just take the difference in the magnitudes. 8g over 5 is bigger, 6g over 5 is comparatively smaller. So 2g over 5 meters per second square. So this is the magnitude of the change in your acceleration. Okay. Question number 5. One end of a light inextensible string of length 4a is attached to a fixed point A on a horizontal ceiling. Okay, a particle P of mass m is attached to the other end of the string. Okay, we can see that the particle is held in equilibrium at a vertical distance 3a below the ceiling. Okay, so they are holding it here in equilibrium with the string taut. Okay, the particle is then projected with speed root 7 ag. Do you see? So this is the place where we start our motion, and then we project it with speed root 7 ag. Okay, in the direction perpendicular to the string. So that means it's directly thrown in this direction perpendicular to the string, which means we immediately start the circular motion. Then as shown in the subsequent motion, the string remains taut. Okay, so in the subsequent motion means while the string is moving, it is remaining taut. Okay, so what are they saying here? Find the speed of P at the instant before it hits the ceiling. Okay, so they say here that this is supposed to what? Reach up all the way over here and what? It's even going to hit the ceiling. So you are supposed to what? Find the speed before it hits the ceiling. So what do we need to do here? Again, in vertical circular motion, there are just two concepts to use. Conservation of energy and F equal ma towards center. So if I want to find the speed before it hits the ceiling, I'll take the particle at this point. So let's use what? Let's use the concept of conservation of energy. So when we use conservation of energy, so what shall I use? GP 0 level at the, you can use B, or I think GP 0 level at the very top is easier. Because to find heights, it's a lot easier, right? At the very top. Okay, so anyway, if your objects are below your GP 0 level, your GP will be what? Negative. That's all. So everything is below, but it's so easy to measure the heights. Okay. So conservation of energy, the energy at the point P is equal to the energy where you hit the ceiling. So what's the energy at point P? What's the energy you have at point P? We have kinetic energy because you can see there's speed, and we also have GP. So we have KE plus we have GP initial. And then equals to what? At the end, do we have GPE? No, right? It's at the GP 0 level. Do we have kinetic energy? I mean, that's what they ask us to find, right? Yeah. Find the speed before he said, because obviously there is some kind of a speed here. So there is a final kinetic energy. Okay, so let's find it. Use the formulas and find. Okay, so initial kinetic energy half mv square. What's your v square? root 7 ag, right? Initial energy is root 7 ag. So when you square it, it will be just 7 ag. Plus Gp is mgh. M into G into what is H? Not 3a. Yeah, you should take minus 3a. The reason being our GP level is below. I mean, our object is below the GP level. Okay, it entirely depends on where you mark your GP level. Just do the whole sum with respect to that point. That's all. Then the next one equals to final kinetic energy is half m v square. So we'll cut off the m value. So we get here 7 over 2 ag minus 3 ag equal half v square. 7 over 2 minus 3 is 2 times 3 is 6. 7 minus 6, that is half ag, right? So we get v square equals to ag. So v equals to root ag. We get v equals to root ag. Okay, so this is the speed of the particle at the instant before it hits the ceiling. Yeah, so this is the answer. Okay, so now let's move on to part B. So part B, you can see it immediately. It has how many marks? 7 marks. So this is going to be a challenge. Okay, so let's read the question. The point B is the lowest point of the path of P. We can see that they mark the lowest point as point B. The first time P passes through B, the tension in the string is T1. The first time. So the first time it passes through B, first time means before it hits the ceiling, right? Before hitting the ceiling, they say the tension in the string is T1. And then they say, and the second time P passes through B, the tension in the string is T2. Okay, how is that happening? Why do you think the tensions are changing? Now, normally we know in circular motion, when we go the full round, we always have the same tension at the same point. But now they say at this point, when you first pass point B, and when you again pass means after you go up and come down again, right? The second time you pass point B, there's another tension they say. So what is the primary reason for that? The speed, yeah, the speed has a role here. Definitely, tension depends on the speed. So the first time the point passes through B, the speed you have, and the second time it passes, the speed you have. Well, what is the main concern here? Now, do you notice here that our particle goes and hits the ceiling? So when you go and hit the ceiling, are you going to rebound back at the exact same speed that you hit? No. So there you get a change in the entire circular motion. The entire equilibrium will change. The symmetry will change, because if it didn't, then this energy is conserved. Normally energy is conserved, but because it hits the ceiling, then the rebounding speed where it comes back is totally different. So because it's different, then when you come down over here, you will have now a completely different speed, which results in what? Which results in giving you a different tension. Which results in giving you a different tension. So they say that second time P passes through with tension in the string is T2. Given that the coefficient of restitution between P and the ceiling. So restitution, do you remember restitution? This is something you learn in M2. When two objects collide, you have Newton's law of restitution, which is equal to what? E equals speed of separation divided by speed of approach. Okay, so that is given. That is given for what? That is given for the collision with the ceiling. They're asking you to find the ratio T1 to T2 in the simplest form. Okay. So what you need to do first is this. Okay, the first thing we can do here is, shall we first find the speed that you pass through B and find the tension 1, because that is the first thing you need to consider here, because that is before you hit the ceiling, right? So after hitting the ceiling, we will consider that mechanism separately. Okay, so before impact with the ceiling, before impacting the ceiling. Before impact with ceiling, let's work. So I'm going to find the initial velocity that we pass through B. Let's say this is okay, let's say this is velocity V, V1. So how do we find? To find the velocity at V1, I will have to use what? The law of conservation of energy. So let's use conservation of energy from P to B. What do we have here? Initial energy, what do we have? You know, you have both KE and GP. What's KE? Half mv square is 7 ag. Plus GP is mgh. H is minus 3a. Do you agree? Equals the final energy at point B. What are the energies you have? You have kinetic energy half mv1 square plus GP. GP is mgh. What is h here? It's directly 4a, right? This is a extensible string of length 4a. And since you are below your GP level, it will be minus 4a. Cut off all the m values here. M cancels out. From everyone, m cancels out. I'm trying to make v1 the subject. We'll multiply the whole equation with 2. Multiply the whole equation with 2. We get half into 2 is 7ag minus 3ag equals v1 square minus 4ag. Sorry. This is, yeah, we multiply with 2, right? So this should be minus 6ag. And 2 times 4, we get minus 8ag. So take everything, all the ages to one side, and I get here v1 square equal plus 8 plus 7 minus 6. 9 ag, right? v1 square is 9 ag. Now shall we find the tension T1? So tension T1 is what? You know, how do you find tension at at the point when it passes the point B? We need to use now what? The next equation we use is F equal ma towards the center. So apply F equal ma towards center at point B. F equal ma towards center at the point B. So at towards center, where is the center? Center is the center of your circular motion. Do you first of all realize where is the center of the circular motion? Center is at A, right? We are doing a vertical circle. The center is at A. Okay, are you listening? So apply F equal ma up. So what do we get here? So when you apply it upwards, also I have not marked one force here, right? Who is that? mg. We have to mark mg. Okay, so then let's apply. So when you mark upwards, what do we get? Tension 1 minus mg equal m. Acceleration we will use now what? Are we going to use r omega square? We actually find we found the velocity at that point. So why go for r omega square? We'll go for v square over r. So you have to substitute the v square value and the r value. The substitute T1 is what we need to find. Minus mg m v1 square we found, which is what? 9 ag over radius was? Our radius was 4a, right? The radius of this radius is 4a. You see? So tension equals, the a to a will cancel out. And you get 9 over 4 mg plus mg, which is how much? 13 over 4 mg. Yes. Okay, so this is the tension before the impact. Okay, so now we have a task to do. What is the task? So now your task at hand is what? You have to now go to the place where we are impacting. Go to the place where we make the impact. We found the speed which we impact. So what do we need to do here? We have to find the speed with which we rebound, because with the rebounding speed, the entire thing is changing when it's coming back. Okay, are you hearing me? So how do we get the speed of rebounding here? 12. Yeah, so then we have this equation in mechanics 2, E equals, if one object is moving and the other object is stationary, like when you hit a wall or ceiling or the ground, the equation we use for restitution is E equals to V over U directly. Speed of separation over speed of approach. The strict equation is necessary to be used if both objects are moving. But here you are hitting a ceiling. So when you are hitting a stationary object, then we use E equal V over U, where V is the speed after the impact and U is the speed before the impact. Have they told you the restitution coefficient? Yeah, restitution coefficient is half. So V is the final speed. Let's say the final speed, that's rebounding speed. Let me name it as, how do we name it? Shall I name it as, we use V1 here, we use V here. Shall I give another letter W? Because I want to use V2 here again. For T2, we are going to find tension 2 here, right? Yeah. So I prefer to have V2. Okay, so because of that, the speed with which we rebound, I'll just use another letter. If you want, use X or Y or something. Okay, so I use W. It's entirely up to you what you use. So V is the speed with which we rebound. I'll say it's W. U is what? The speed with which we hit the ceiling. Okay, so that I think we found that V value, right? What was V? Root AG. V was root AG. So take the root AG here, we get half of root AG. W is equal to half of root AG. So now what do we do? So now with this particular speed, you have to again find what? You have to again find the velocity that you reach point B. Because you need to realize now when you're coming back, now the object is coming back with the speed W, right? It comes back with the speed W, and when it comes to the point B, definitely the velocity is different because now your starting velocity is different for this part. So I'll say this is V2, and at this point the tension they have mentioned at the second time it's coming down, the tension is T2. That's what they've told us. They've told us T2 is the tension as it goes through the second time. Second time it passes through, the tension is T2. Okay, first things first, we have to find what? The velocity. The velocity at point B. We need to find the T2, or the velocity, V2. So how do we find V2? Again, you use the law of conservation of energy. So by the law of conservation of energy, initially what energy do I have at the top? I have kinetic energy with W, right? Half mW square. I'm using conservation of energy. Half mW square plus, do I have GP at the very top? No. At the bottom, what do we have? Kinetic energy, half mv2 square. And what about mgh? We have it, right? Mg into what? What's the height? Minus 4a. Remember, it's minus because we are below our GP 0 level. Okay? M is common to everyone. Remove the M. And we'll multiply, okay, we have W square. So let's get W square here. Half into W square will be 1 over 4. Half square is 1 over 4. Root AG square is going to be just AG. Do you agree with me? This is half V2 square. This is minus 4GA. Multiply everything with 2 to get rid of the half in V2. So I get here 1 over 4AG equal V2 square minus 8AG. 1 over 4AG plus 8AG, what is the speed V2? What is the V2 square value? 1 over 4 plus 8AG. How much? 33AG over 4. Yeah. So this is V2 square. Now what do we do? Now again apply F equal MA towards center. So what are the forces we have towards center? So here also don't forget we have the mg weight. So what are the forces towards center? T2 minus mg equal mv square over r. So input the values. Tension 2 minus mg. mv2 square over r is 4a, right? So v2 square is 33ag over 4. V2 square is already given me. Yeah, so we don't need to square. This is V2 square already. So directly put the value. Yeah, we can cancel off the A to A. And then I get here tension 2 is 33 mg over 16 plus mg. 33 over 16 mg plus 1 mg is? So we get 49 over 16. So they're asking you to find the ratio T1 to T2. So T1 was, how much did we get for T1? 13 mg over 4, 13 over 4 mg to 49 over 16 mg. So it's a ratio. Cut off the similar terms, mg cancels. And then we could multiply both sides of the ratio by 16. We could multiply both sides of the ratio by 16. Then what by 16 times 13 over 4 is 52. And this one 49 over 16 into 16 is 49. 52 to 49. This is not simplifiable. We can't simplify it more than this, right? So the simplest ratio is 52 to 49. Okay, moving on to question 6. A particle P of mass 0.4 kilogram is attached to the midpoint of a light elastic spring of natural length 0.8 meter and modulus of elasticity 20 newtons. Okay. The ends of the spring are attached to the fixed points A and B on a smooth horizontal table. Okay, so we have a horizontal system here. There's a horizontal table. So you have a horizontal table, and on either side of the horizontal table, you have the points A and B. So A and B are on the two ends, and they say where AB is 1.2 meters. So if AB is 1.2 meters, what do you think? What's happening here? It gets stretched, right? Because it's 0.8 is a natural length. So AB is 1.2. It automatically it's stretched, and they say here this particle P is attached to the midpoint of the elastic spring, isn't it? So it's attached to the midpoint. So you have your spring. You have your spring, the particle is attached to the middle. Actually, since this is a horizontal system, if you want, you could draw the spring by using a line even. Okay, but okay. So anyway, the object is attached to the midpoint of the spring, which means what? Which means when you attach the object to the midpoint of the spring, we are going to consider this as not a single spring now. We are going to consider this as two springs. Okay, so each spring will have natural length how much now? The whole thing was 0.8. So when you attach the particle to the middle, can you see? When you attach the particle to the middle, the length, the natural length 0.8 will be 0.4 meter for each part of the spring. Are you with me? And then the lambda is the modulus of elasticity, that will not change. Lambda is 20 newtons. Okay. So your lambda value is 20 newtons. The ends of the springs are attached to the fixed points A and B, where AB is 1.2. Initially, P is at rest at the midpoint of AB. Are you with me? So initially, what's happening? When you draw this diagram, initially, okay, so A and B are the 2 points. The particle is initially in the middle. Okay, it lies on the table, it touches the table. Initially, it's in the middle. Okay. Initially, it's in the middle means what? It's at the distance of 0.6 meters. Are you with me? Draw a clear diagram. 0.6 meters. Are you with me? Okay, so 0.6 meters either side. Natural length of each spring is? Natural length of each spring is 0.4 meters. Okay, so this is the natural length. Okay, are you with me? So what are they saying here? They say, okay, initially particle P is at rest at the midpoint O. So midpoint is named as O. Give it the name O. Midpoint O of AB, where AOB is a straight line. Can you see AOB is a straight line? The particle P now receives an impulse of magnitude 2 Newton seconds, so that P starts to move directly towards B. So we give an impulse. There is a force. So what happens? The particle will now start to move directly towards B. Are you with me? Okay, so then the first thing when you learn about this SHM, the first thing is, you know, when the particle is in equilibrium at a certain point and you disturb it from its equilibrium position, that equilibrium position is what? That equilibrium position is the center of your simple harmonic motion. Always. So this is the place where the particle was in equilibrium. So now you are disturbing it from its equilibrium by providing this impulse. So anyway, the place where the particle is at rest, that is the place where the particle prefers to stay, that is the equilibrium position. Or else, in other words, the center of your SHM. Are you with me? So then we are supposed to what? We are supposed to prove that P moves with SHM. So how do you show that the particle moves with simple harmonic motion? So basically, to prove the particle moves with SHM, you have to prove an equation of the type x double dot equals minus omega square x, isn't it? So how do we prove it? So you take your object at a general point, isn't it? Consider your object at a general point and mark all the forces. So I'll say the object is over here, general point. How do we measure the distance? The distance is measured from the center of the SHM. The distance is measured from the center of the SHM, away from the center. We measure the distance x. Are you with me? If x is this way, x double dot is also measured in the same direction as x. Okay. So what force? I mean, what equation are we going to use? We are definitely going to use F equals ma. What are the forces acting on this particle at the general point? What are the forces acting on the particle at the general point? Yeah, tension. You have tension from spring A and tension from spring B. There are two tensions horizontally. Tension from spring A and tension from spring B. What else? You have its weight and normal reaction. Actually, since the particle is moving horizontally, weight and normal reaction, will it make an impact? No. Normal reaction is vertically up, weight is vertically down, but they will not make any special impact because we are considering horizontal movement. Okay. So I will mark them. So what equation are we, before we go to use F equal ma, first thing is find the tension A and find the tension B. Are you with me? Find the tension A and tension B. Let me erase this particle over here. Okay, so now the particle is over here. So I dribble like this. Okay, so this is your center. Okay, how do we get the tension? And normally tension is equal to what? Lambda x over L, isn't it? Tension is lambda x over L. Lambda is known. Lambda is 20. And what do you mean by x? In a spring or extensible spring or spring, x is the extension, the amount of the distance that you have moved beyond your natural length. So are we going to say the extension is simply just the x value here? No, when you consider the spring A, do you see that from this point A until this general point, it has, I mean, there's quite a distance here. Can you see? So how much is the extension? 0.6 plus x? No, it's beyond the natural length. The length that you have moved beyond your natural length. So this natural length is not part of the extension. 0.6 is this length. From 0.6 you subtract 0.4 and you get this length, which is how much? 0.2. So this 0.2 is also extended and plus x distance. And this 0.2 plus x is the extension of spring A. 0.2 plus x. Divide by natural length is of the spring is 0.4. So this is tension A. Similarly, get tension B. Tension B is lambda x over L. So lambda is 20. How much is x? How much is the extension of spring B? Look at it very carefully. Now spring B, I think you can see there's a shorter extension because you only have this short distance. How much is this extension? How do you get this distance? This amount. Because this is the extension. Do you see it? The natural length, and this is the amount it has extended beyond the natural length. So this, you can get this full distance. Yeah. Okay, so again, we know that this distance is 0.6 minus 0.4, this 0.2 distance, isn't it? So from 0.2, you have come a x distance behind, isn't it? So this short distance is 0.2 minus x. This short distance, 0.2 minus x. The extension of spring B is 0.2 minus x over natural length is 0.4. Do you agree with me? So now it's a matter of using F equals MA. So we will use F equals MA away from the center. So what do we get? Force away from the center. Tension B, right? Tension B is away from the center. Tension A is towards. So TB minus TA. Mass is 0.2. Have they told you? Mass is 0.4. Acceleration is the x double dot. Okay, and then we are trying to prove the object moves in SHM. So basically, we are trying to get the equation of the format x double dot equal minus omega square x. Are you with me? Okay, so tension B is lambda. Tension B is lambda. Sorry, we found the tension B value. Input the value 20 times 0.2 minus x over 0.4 minus tension A is 20 times 0.2 plus x over 0.4 equals 0.4 times x double dot. Are you with me? Simplify. 0.4 is a common denominator. Shall I take 0.4 as a common denominator? I get here 20 into 0.2 is how much? 20 into 0.2 is 4 minus 20x. Minus 20 into 0.2 is minus 4. Minus 20 into x is minus 20x. Am I correct? Yes? What happens? The plus 4 minus 4 cancels off and you get minus 20 minus 20 is minus 40 divided by 0.4x equals 0.4 x double dot. So there's another 0.4 that comes down here. X double dot equals minus 40 over minus minus 40 over 0.4 into 0.4. And I know how much this sounds is x equals minus 40 divided by 0.4 into 0.4 is minus 250x. So x double dot equals minus omega square x. Can we get an equation of this type? So if you are capable of creating an equation that looks like this, it means your particle moves in SHM. So you can write therefore particle moves in SHM. Okay, is this clear? So part B, they tell you write down in terms of phi the period of the motion. How do you get the period of the motion? Period equation is periodic time. Periodic time equals to what? There's an equation you have to remember 2 pi over omega. Right? So we just now found the omega value. X double dot equal minus omega square x. What was the omega square value? You can say 250 is the omega square value. X double dot equal minus omega square x. So omega is the square root of 250. So 2 pi over square root of 250. Okay, so this is your periodic time. You can keep it like this. You could simplify. 0 point, how much? You could keep it as 2 pi over root 250, no problem. Or what did you say? How much was it? A root, this simplifies into a simpler form, right? How much? Root 10 over 25 pi. Simpler form. Okay, this is better. Okay. Part C. You could keep it to 3 years or else it's better to keep it in the exact form here. Part C, find the amplitude of the motion. How do we find the amplitude? How do we find the amplitude? Normally, amplitude is the how much you move away from the center of your SHM, right? Now they tell you at the beginning, and when the particle was at the center, they gave a they gave an impulse of 2 Newton seconds, isn't it? They gave an impulse of 2 Newton seconds. How do you now? You can see I have come down to part C, but I have so far not used this impulse anywhere at all. How does this impulse play a part in this question? Why have they given you the impulse? What can you find by using this impulse? You do realize that at the center of the SHM, when the particle has a certain speed at the center, that speed is what? The speed that you have at the center of SHM is the what speed? It's the maximum speed. The maximum speed is obtained at the center of SHM. So when you go towards the amplitude, you get slower and slower, and at the amplitude, your speed becomes 0. So basically, the moment you provide the 2 Newton seconds, that's when you are at the center. So what's the impulse equation? You are aware impulse equals change in momentum. I equal mv minus mu. So this particle was initially at rest, isn't it? You consider this particle, it was initially at rest. They gave an impulse of 2 Newton seconds. They gave an impulse of 2 Newton seconds. So what happens here? So impulse equals to mv minus mu. We are trying to find the speed of the object. At the beginning, the speed was 0. After the impulse, there is a certain speed. So let's find the speed. Impulse is 2 Newton seconds. Mass was how much? 0.4. Final velocity is what we are trying to find. Initial velocity 0.0. Can you see that I'm finding the speed of the object immediately after giving the impulse? How much is the velocity immediately after giving the impulse? How much? 5 meters per second. 5 meters per second. So this 5 meters per second is going to be the what speed? That 5 meters per second is achieved at the center of SHM, right? The moment you provide the 2 Newton second, that 5 meter per second is the speed at the center. So when you have the velocity at the center, that means that's the maximum velocity. So you have the maximum velocity in SHM. Vmax is 5 meter per second. How do you make use of the Vmax? You get Vmax when x is 0, isn't it? At the center, x is 0. So what equation do we use? We use V square equal omega square a square minus x square. V square is 5 square, omega is root 250, omega square is directly 250. A is the amplitude which we are trying to find, x is 0 because the maximum speed occurs at the center and x is 0. So this is 25 divided by 250 equals a square. Do you agree? How much is it? 1 over 10 equals a square, which means a is root 1 over 10 or root 10 over 10. Or equivalent decimal is how much? You could keep it like this, 3.0. Oh, yeah, or let's keep it to exact. Better to keep it in exact. Okay. The next part, amplitude is done. Find the length of time in each complete oscillation for which AP is greater than 0.5. Okay, so you're supposed to find the length of time in a complete oscillation where AP length is higher than 0.5. Okay, so what are we basically finding? AP is higher than 0.5. How do we find the length of time where AP is greater than 0.5? Okay, so moving on to part B, I'll read it again. Find the length of time in each complete oscillation for which AP is greater than 0.5. So I think I redrew the diagram again because I see that my natural length is like slightly off with the extension 0.2 here. So that is perfectly fine, okay? But I just drew the diagram again. So the natural length is 0.4, the extension to the center is 0.2. Can you see? So now they tell you here, you have to find the length of time in each complete oscillation where AP. So starting from AP should be more than 0.5 meters. So this is the place where from A we measure 0.5. So you can see its natural length is 0.4. And then one more, and then the 0.1 meter when you travel, this is the 0.5 meter boundary. So you have to basically find the amount of time the particle is spending oscillating over in this side. Are you with me? So over when you pass this point over here, you're supposed to find how much time the particle spends oscillating over in this side. Okay, so we know that the amplitude, we found the amplitude was root 10 over 10. What's the decimal figure? 0.316. Okay, 0.316 meters. Okay, correct to 3 dB. So you can see here, definitely, you realize that the particle is going to go 0.316 meters from the center to the left side, to the right side, and also it comes back and again goes 0.316 meters to the left side, right? So that's what happens. But the task here is that you find how much time the particle is 0.5 meters away from AP. Okay, so find the length of time in each complete oscillation for which AP is greater than 0.5. So basically this part. So this part of the how much time does it spend over here? Okay, in this section, somewhere like over here, right? Because the amplitude is 0.316, so comes until somewhere over here. Okay, now how do we find the time? So to get this time, I'm going to break this section into two parts. I'm going to break it up into two parts. Okay, so this is my amplitude. Let me mark this as amplitude. Okay, so this is the amplitude. Okay, this is the amplitude 0.316 root 10 over 10. So let's say we'll take the object from over. I'm going to find the time taken first for this duration. Okay, in this duration, how much time is taken for this duration? Coming from the amplitude towards the center. If you take it for one direction from the amplitude towards the center, how much time will we take? You know the total time taken for the entire oscillation to go from from the center to the amplitude and back again from the amplitude to the center and then to go to the right side and again come back. The full time periodic time is capital T. So do you you need to remember that the time taken to come from the amplitude to the center is what? A quarter of the periodic time. Do you agree with me? So one time here is a quarter of your periodic time. Plus, let's find the time taken for this part. How do I get the time taken for this part? This section. So for this one, I can find the time using x equal a sine omega t. X equal a sine omega t gives you the, when you start your movement from the center, you use x equal a sine omega t. So I will use x equals a sine omega t and get the time duration for this small section. X is 0.1, the distance moved from the center. Amplitude is root 10 over 10. Use the exact figure. Sine omega. Omega was root 250, which was how much? 5 root 10. Sine omega t is the t1. So let's simplify. This is 0.1 into 10. 0.1 into 10 divided by root 10 equals sine 5 root 10 t1. Are you with me? So how much is 0.1 into 10 divided by root 10? How much is it? How much? Root 10 over 10. Sine 5 root 10 times t1. So get it. This is sine inverse root 10 over 10 equals 5 root 10 times t1. Are you with me? So 1 over 5 root 10 sine inverse root 10 over 10. Okay, is that, do you get what I'm doing here? Okay, so this is the time one. So this is the time taken to go from the center to this point. Now, and then get the T over 4 value also. The time taken for the yellow color part to come from the amplitude to the center to capital T was, how much was capital T? We found in part B, capital T, periodic time is 10 root 10 pi over 25. You should divide by 4, right? T over 4 or into 1 over 4. Can I know how much is this answer? Root 10 pi over 25 times 4 is 100. Okay, so now how do you find the length of time that it is length of time? AP is greater than 0.5. How do you get the length of time? So you know the length of time is greater than 0.5 meter is when it's let's say consider the particle is coming from this corner for an instance. So it comes over here, it completes a quarter of the periodic time. Then it comes over here, and this time duration also it's the T1 time duration. But then over here, after you come to this point, you know that your particle will travel backwards, right? But this time duration, are we counting? No, we don't count this time duration. Then you come to the amplitude over in this side, and then again the particle comes back, and then do we consider this time duration again? No, and then you come over here where AP is 0.5, and from here we again count the time. So it's coming back, returning journey. Okay. So over here, what do you think about this time duration when you come back? Will it be a different time duration or the same time as T1? From the center to come to this point, and from this point, if you are coming back to the center, the time taken is exactly the same. Okay, so it's symmetric. This time over to come from center to this point, to move 0.1 meter away from the center, and to come from a 0.1 meter away from center towards the center, the time taken is exactly the same. And then again, you travel the whole, again, you travel a quarter of your periodic time. Can you see? Then you have completed one full oscillation. So you can see what you need to do here is you add the quarter of your periodic time plus the T1 values and just what? Multiply it with, add those two T values and multiply by 2. Okay, then you get the amount of time that you are 0.5 meters away from where AP is greater than 0.5. So you add the two time durations, root 10 pi over 100 plus 1 over 5 root 10 times sine inverse root 10 over 10. They want this, the time is greater than 0.5 in a single oscillation, right? In a complete oscillation, yeah. So in a single oscillation, so how much time is it away? So times 2. So I get here root 10 pi over 50 plus 2 over 5 root 10 sine inverse root 10 over 10. Calculator must be in radian mode. With your calculator in radian mode, type this and get the answer. So getting a time, so your angle unit must be in radians. Root 10 pi over 50, 2 over 5 root 10 sine inverse 0.2393, yeah, 0.239. So this is the answer. There are other multiple ways of getting this answer as well. So any other person could also use the x equal a cos omega t and get the time taken to travel from the amplitude to this distance and times it by 2 and multiply and subtract it from the full periodic time, capital T. That's also correct. So there are many other ways of getting this answer as well. This is one way. So, so anyway, you whatever the technique you apply, as long as you do it correctly, you should end up with this 0.239 seconds answer. Okay. Okay. So now let's move on to question number 7. Okay, so question number 7, they say figure 3 shows part of the curve C with the equation y equal x square plus 4. The shaded region R is bounded by C, the line with equation x equal 1, the x-axis, and the line with equation x equals 2. The unit of length on each axis is 1 centimeter. Okay, so they have told you the units are in centimeters. A uniform wooden solid S, okay, a uniform wooden solid S is made in the shape form by rotating the region R through 360 degree above the x-axis. Okay, so if you rotate the region R 360 degree around the x-axis, you are going to create what? A 3D solid. You are going to create a 3D solid. Do you agree with me? So the two ends will give the two circular faces. Do you agree with me? I'm just drawing to give you an idea. So you get a solid shape like this. You rotate 360 degree, right? So a uniform wooden solid S is made in the shape formed by rotating the region R to 360 degree above the x-axis. So this kind of shape. Using algebraic integration, show that the volume of S is 613 over 15. Okay, what's the formula to find the volume? Remind me the formula to find the volume. This is the Cartesian equation. To find the volume, what's the equation we use? Volume equals pi y square dx. Pi y square dx. This is the equation you learn in P4 as well. Volume equals pi y square dx. Your limits are from where to where? From 1 to 2. Do you agree? Okay, so let's integrate. So we input the value. So pi y square. What's the y square value? So your y value is x square plus 4. So you are going to square it. So let's first, before integrating, let's open the bracket. X square, when you x square plus 4, when you expand x to the power 4 plus 8x square plus 16, right? With respect to x. So when you integrate, now you are ready to integrate. So when you integrate, you get x to the power 5 over 5 plus 8x cube over 3 plus 16x. Do you agree with me? And your limits are from 1 to 2. Okay, let's input the limits. What do we get? So we get 2 to the power 5, which over 5. 8 into 2 to the power 3 over 3 plus 16 times 2 minus 1 to the power 5 over 5 plus 8 into 1 to the power 3 over 3 plus 16 times 1. How much is this? How much is this? It's valid? 896 over 15. The other part minus how much? 283 over 15. Subtract 896 over 15 from 283 over 613 pi over 15. Are you okay with that? That's to show that. That's to show that for part A. So Roman number 2, they say find the three significant figures, the distance of the center of mass of S, the solid. The distance of the center of mass of S from O. Okay, so how do we find the distance of the center of mass? Okay, how do you find the distance of the center of mass? So this is a 3D object. To find the center of mass of a 3D object, we have a equation defined in the textbook, right? However, you do know when you are having this 3D solid rotated 360 degree around the x-axis. What about the y bar? Do you have? You can see that the x-axis is a line of symmetry, isn't it, for this object? Thereby, y bar will be 0. So the center of mass coordinate will only be obtained by the x coordinate. Can I have the x bar equation for 3D objects? There is the equation x bar equals integration of pi. No, it's y. Okay, tell me. Y square x dx over y square dx. Okay, so basically, actually, both these equations originally had pi, and then it cancels out. That's why it's not there over here. Okay. So then the thing is the integration of pi y square. Do you see the integration of pi y square? We have already found as 613 pi over 15. So that's the denominator part is done. We have to just get the numerator part. Okay. So let's integrate. So shall we integrate this? The limits are from 1 to 2, right? So we'll take the numerator and let's get the value of y square x. So y square is y value is x square plus 4. So this is y, you square the whole thing, multiply by x with respect to x. What do we get then? Integration mark is still there. Expand the bracket, x to the power 4 plus, when you expand 8x square plus 16. And then you multiply the whole thing with x. This becomes x to the power 5 plus 8x cube over 3 plus 16x. Okay, so now it's time to integrate. So what happens when you integrate x to the power? Oh, sorry. This is 8x cube. Yeah, x to the power 4 into x is x cube, x to the power 5, 8x times x is 8x cube plus 16. Yeah. Okay, now we are going to integrate. Yeah. So when we integrate x to the power 6 over 6 plus 4 over 4 plus 16x square over 2, and your limits are from 1 to 2. So let's input the values. So I get here 2 to the power 6 over 6 plus 8 into 2 to the power 4 over 4. 16 over 2, actually we can simplify. And then minus 1 over 6 plus 8 into 1 to the power 4, that's 1. 16 over 2, because basically when you multiply with 1, there's no change. Can I know the value of the first bracket? 220 over 3 minus 61 over 6. And the answer is 129 over 2. Is that clear? Yeah. So now what we do is we have to get the x bar. So to get the x bar, you have to get this value, substitute, right? So x bar coordinate is pi. The pi actually cancels out, but the reason I'm using the pi here is because we have got pi y square in part A. Okay. So pi y square x answer we found, right? Pi y square x answer was how much? 6. This answer 129 over 2 on the numerator. 129 over 2 divided by the pi y square answer is what we got in part A, 613 pi over 15. Are you with me? The pi will immediately cancel out. So you get here x bar equals 129 over 2. The 15 is on top, 613 is down. Is that okay? How much is the x bar? 1935 over 1225, which when you make it to 3SF, 1.578 to 1.58 what? Centimeters, because they told in the question this units are all measured in centimeters. Okay, is that clear? Yeah, so this is 1935 over 1226 here, right? Okay, so give the values correctly, 1226, which when you take it to 3SF, 1.5783. So when you take it to 3SF, it's 1.57. Okay. The next part. Okay, so look at the next part. They say here a solid S1 is formed by removing a solid cylinder of radius 3 centimeters and length 1 centimeter from S. Now you can see this solid S is what we got from the part A, right? Part A, you can see the solid S has 1 to 2, so the width was 1 centimeter, right? So they are saying here a solid S1 is formed by removing a solid cylinder. So from your S1 figure, you remove this cylinder of radius 3 centimeter and length 1 centimeter from S. A metal cylinder of radius 3 centimeter and length 1 centimeter is placed in the resulting hole to form a new solid. Do you get what they are doing? They are removing a cylinder, they are removing the cylinder from this object, and they are inputting a new cylinder which is made out of a new substance. Okay, so the densities are different. Mass densities will be different because it's not made out of the same material. We can't take the mass ratios by using volumes. Okay. They say the axis of the metal cylinder coincides with the axis of symmetry of S1. As you can see, the way they have removed the cylinder is so that the axis of symmetry is the cylinder is removed exactly to be symmetrical around the axis of symmetry. Okay. The point B is the center of the smaller plane face of T. Okay, they have marked it. The mass per unit volume of S1 is M. S1 is the solid S1 is formed by removing the solid cylinder. So when you remove the solid cylinder, this remaining part is having what? They are saying it has the mass per unit volume of S1 is M and the mass per unit volume of the metal cylinder is 5M. Okay, the mass per unit volume. Find the distance of the center of mass of T from B. You have to find the center of mass of this compound object from T. How do we do that? So let's do the typical diagram. You have to identify your object, the mass, and the center of mass. Look. Okay, so I will identify the object mass and the center of mass. So the first object is what? The first object is the complete solid S. Right? Solid S was, how was it? You had this solid S in this manner, right? So this is the solid S. What is the mass of solid S? Now, you know, they have told you we are going volume is, they have told you mass per unit volume, right? We are going with mass per unit volume. So what's the mass of solid S? We found the volume of solid S, didn't we? Show that the volume of solid S is 613 pi over 15. Can you see? So solid S mass is 613 pi over 15. Are you with me? And didn't we find the center of mass of solid S as well? Before going to center of mass, the mass is not complete. This is the volume. How do you make it the mass? They have told you the mass per unit volume of S1. Now S1 is made up of the same material as S, right? Because S1 is made from when you remove the cylinder from S. Okay. So how much is the mass? The mass per unit volume of S1 is M, which means per cubic centimeter it's M units in weight. So I will use here this multiplied by M. So the volume you multiply by the mass per unit volume and then you get the mass. Center of mass coordinates. I think you saw we got the center of mass coordinates 1.58. So but however the center of mass coordinate is measured from where? It was measured from the origin, right? From this origin. So now you can see that we are considering the center of mass from the point B. Point B is over here. Do you see? This is point B. So if you are going to give your X bar, how much is the X bar figure? You have to take your the previous answer and subtract 1, isn't it? From this answer, don't take this less significant answer. Take the bigger answer. Then you'll get the X bar value. How much is it? 1935 over, how much was it? 1935 over 1226. Subtract 1. How much is it? Okay, that's correct, right? 709 over 1226. So this gives you the distance of the center of mass of this solid S from, not from the origin, but from this point B. Okay, because we are going to measure the center of mass now from point B. Are you with me? Okay, then the next one. What should be my next object that should be considered? Who is the next object to be considered? The cylinder that you are taking out. The cylinder that you are taking out. The cylinder that you are taking out. So we know it has a radius of how much? 1, right? Radius of 3, sorry, radius 3 centimeter, length 1 centimeter. So radius 3, length 1. These are all going in centimeters. Okay, so then how do we get the mass? The mass of a cylinder. First of all, they go with volume of a cylinder. What's the volume of a cylinder? Volume of a cylinder is 5 r square h. 5 r square h. So use here 5 r square h. And here don't convert the r and h to meters because they say in this question the length of the each axis is 1 centimeter. So basically we have got here everything in cubic centimeters. Okay, so per cubic centimeter, how much is it? Pi r square is 3 square, h is 1. And what about the mass per unit volume? Is it m or 5m? Is it m or 5m? This is the metal cylinder, or is this the one that you remove? This is the one that you remove. This is the one you remove. So therefore, it's made up of the same material as this object, which means mass per unit volume is S1, m. So then you multiply this with m, which means the mass is 9 pi m. And then let's get the center of mass. Center of mass of a center of mass of a cylinder is exactly where? It's exactly in the middle. So we know this is the point B. We are measuring the center of mass from this point B, right? So the length is 1 centimeter, which means the center of mass is at a distance of just 1 centimeter, 0.5, half of 1. Are you with me? Everything is in centimeters. Okay, is this clear? What about, do we need to input the y coordinate? No, right? Because the object is symmetric around the x-axis. So when you are symmetric around the x-axis, you can see I'm only writing the x coordinate. There are no y coordinates because y bar is 0. Okay, then what's the next figure that I should input here? From this object, you remove this cylinder, and now in place of the cylinder, what do? You input a metal cylinder. So this is what you remove, right? This is the one you remove, and this is the one that you add. What do you add back? You add back a metal cylinder. The radius and the length are exactly the same, right? Okay, so pi r squared h. And then this time, because it's the metal cylinder, you multiply the mass per unit volume of the metal cylinder is 5m. Can I have the answer here? Pi 3 square h into 5m. How much is it? 9 times 5? 45. H is 1 here, right? 45 pi m. Are you with me? And what about the center of mass? Same, because it's a cylinder, center of mass is exactly in the middle, 0.5. And then the final figure. So in the final figure, what do you get? You have the full solid, right? You remove the cone. Sorry, you remove the cylinder. And you input one back. Are you with me? Okay. Okay, so now let's get the total mass. What's the total mass? What's the total mass of this object now? 613 pi over 15 m. You subtract the 9 pi m and you add the 45 pi m. So do it 613 pi m over 15. You subtract 9 pi m and you add 45 pi m. So you cannot type pi and m in the calc. Pi and m is common. So you just type the other part, 613 over 15 minus 9 plus 45. You can give the pi if you want, but since pi and m are common to both, you can just type the figures. 15 minus 9 plus 45 gives me 1153 over 15 pi m. Is that okay? And the center of mass is what we are trying to find, right? Center of mass is what we are to find the distance of the center of mass of P from B. That's what we are trying to do. Are you with me? Okay, so let's now we have the table. I have calculated the masses and the center of masses. It's now a matter of multiply mass into center of mass. Just multiply. So what do you get here? 613 pi m over 15. You multiply with the center of mass coordinate. 709 over 1226. Multiply the mass and center of mass. This, the cylinder that you are removing, the mass, center of mass multiple is what? Is it addition or subtraction? It's a subtraction. So minus 9πm multiplied by 0.5. The other one, 45πm and 0.5 is the addition. 45πm into 0.5, and then this is equal to the total mass, right? 1153 πm over 15, over 1153 πm over 15 into x bar. Are you with me? The new x bar. Okay, so let's first remove the variable that's common to everyone. Pi and m is common to everyone. Do you agree? Shall we remove that? So then I end up with this figure, 613 over 15 into 709. You don't need to write this step actually. Okay, so it's a matter of typing in the cal now, isn't it? So give the value 613 over 15 times 709 over 1226 minus 9 times 0.5 plus 45 times 0.5. Shall we get that answer first? Yeah. If you double check your answer, okay. Yeah, 6 minus 9 plus 45 into 0.5. This gives me 1249 over 30. Over 15 x bar. So when you make x bar the subject, the new x bar, 1249 times 15, 30 times 1153. Are you with me? 1249 over 30. Sorry, 1249, we'll do it at once. Into 15 over 30 times 1153. So I get 1249 over 2306, which is 0.5416. Yeah. 1249 over 2306, which when you give the previous step, 0.542 centimeters. So this is the distance of the center of mass of P from B. Okay, this is clear. Yes. So this is the end of this mechanics paper.